Hello. This lecture will cover pages 207 through 210 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 12H, Bode Plot example number 4. We're going to start out on page number 207. And I want you to look at example number 4. I'm giving you a transfer function up here. And the transfer function I'm going to give you is 0.25 times the quantity s plus 0.2 divided by the quantity s plus 0.05. Now, I could have given you this transfer function originally, or I could have given you this transfer function here originally. But neither of these are in a form that you could use because I don't have this in a time constant form. The constant k0 isn't a 0.25. Okay? It isn't. Now, this may be in a time constant form. I'm sorry. This is in a time constant form, but the time constant here is the 5 seconds, and the time constant here is this 20 seconds. Notice in this, this could be a mechanical system here where the time constants are real long. So you end up with these break frequencies here being 0.2, like I talked about before, and 0.05. So these break frequencies are really going to be small. But if you're controlling a mechanical system electrically, you're going to have, this is what you're going to be working with, a transfer function that looks like this. So I may have 5 seconds here, and I may have 20 seconds here, but to do the Bode plots, we don't use the time constant. We have to get it in this form here. So whether I give you a time constant, transfer function looks like this or like this, you have to get it in this format right here. So my k value, notice, is 1 here. My k0 is a 1. So this is where I start my transfer function for t of s. Whether I give you this on an exam, whether I give you this on an exam, you get them both into that form. We did that a while ago. k0 is equal to 1, therefore dB is 20 times the log of 1. 0 dB contribution from the k0 term. My first break frequency, if you take a look here, my lowest break frequency is my first one. It's 0.05. It's 0.05 radians per second. It's a pull. It breaks down. My second break frequency is 0.2. My second break frequency is 0.2 radians per second. It's a 0. It breaks up. I could have had a third or a fourth break frequency, which we're going to have in a later example, but up to now, we just kept either one break frequency or 2 break frequencies just to get these first 4 examples out of the way. So what's the general shape of this curve going to look like? Well, it's going to be at 0 dB of this Bode plot. It's going to be coming across, and then you're going to hit, first thing you're going to hit is a pull. It's going to break down. It's going to break down. And then the next break frequency is going to be a 0, so it's going to go from a plus 0 to a minus 1. And then you're going to add another pull, which adds a plus 1, which takes that back to plus 0. So the shape is going to look like this. It's going to break down. You're going to add a 0. I'm sorry. That's going to take it back to 0. So at this pull, you break down. When you get to this 0, it takes that break out, and you break this way once you add them all up and get the composite waveform. So that's what the shape's going to look like as a check. You better end up with that when you're done. So let's look at the Bode plot. How did I do the Bode plot? Again, I labeled this example 4, magnitude plot. My transfer function I wrote over here. I put all the pertinent information on the log paper. I noticed that it's just going to be, I know from my shape it's going to be breaking down, so I put my 0 dB axis high. In my gain, I go minus 10, minus 20, minus 30, minus 40. And then I have to lay out my horizontal axis. Well, my first break frequency is at 0.05, so the unity below that is 0.01. I'm interested in the unity below these break frequencies, don't forget. So if I'm at 0.05, I have to label this down here, and I come in 1 division. I could have come in 2 divisions and done it. You're no problem with that, because I've done that in the first 2 examples. But I'm going to come in 1 division, and I'm going to call that my 0.1. I'm going to call this 0.01. So my 0.01 is here because my 0.05 lays out in here. if you look up above here. So that makes this 0.01. I go a decade down, 0.001. I go a decade up, 0.1, 1, 10. I do my individual contributions on my magnitude plot. 0 dB because of the constant. I put a dashed line the whole way across here. What's my contribution because of my first break frequency being a pole? Well, my first, if you look at that and you're just doing dotted lines now, it's going to come over until you get to the first break frequency, which is 0.05. So I had to label that in down here. We're not at the unity points, we're at 0.05, and at 0.05, it starts breaking down. So I go from 0.05, and I have to come out here to 0.5, because, oops, I have to come out to 0.5, that's my decade. I have to go a decade. In 1 decade, it has to break down 20 dB per decade. So I have to put a point right there, an X right there. At 0.5, I should be at minus 20 dB per decade to get my roll off, and there's my 2 points. I don't need to come down minus 40 and go out here at 10 now. I mean, it's going to go through that naturally. Or, I said that wrong. If I go a decade up from 0.5, I go out here to 5. I don't have to go out to 5 and come up to minus 40. Right there. I don't have to do that because I already got my 2 points. So I get my straight edge and I put my straight edge in. I put a dashed line down through there. Now what about my 0? What's my contribution because of the 0? The 0.2. Well, I come out to 0.2. So I come the whole way out to 0.2 and it's going to be 0 dB. And at a decade above that, I have to be at plus 20 dB. I didn't put that on here, but this is my plus 10. Here's my plus 20 up here. So if I'm at 0.2, I have to go out here to 20, which is that point right there. When I'm at 20, I have to be right at plus 20 dB. Because I go up 1 decade from here. 1 decade from here is that point. And the 0 is putting in a plus 20 dB per decade. So I get a straight line, and I put the straight line in like that. Now I have to add all these up. So I come across here. My pole kicks in, and my pole is going to go down until I hit that point right there. Until I hit 0.2. When I hit 0.2, that's when this is going to break. That's when my 0 takes effect. So I'm taking the composite between this and this, which gets me back to 0. If you notice, I didn't even put this individual component for the 0 in because I knew it broke at this point and it took this out. So I knew it would come back this way. The author has you go ahead and put this in so it shows you the individual components of this overall magnitude. But there's my dB axis. It comes over until I hit my first pole. It breaks down until I hit my 0, and then it breaks over, and there's my solid line that represents the magnitude plot. And phase, there's my phase plot. How do I get that? Well, I label my 0 degrees, and then I go plus 45, plus 90, minus 45, minus 90. I lay out my radians per second exactly the way I did over here. I put my thought in at this point. Once you put your thought in here, you just transfer this down to the phase plot. Let's look at the individual components. And I have to go back and I have to be looking. That's why I just write this stuff here. I can see everything right here. My K0 term is 1. It's a real number. It's an angle of 0 degrees. So I put a dashed line all the way across. That's the angle for my K0 term. It's 0 degrees. What about my pole? What's the first thing I hit? The pole's the first thing I hit. Right here, the break frequency, 1. It's at 0.05. So I go to 0.05 now. I'm not at 0.01 or 0.1. I'm at 0.05, and I come up, and it's a pull, so it has to be down 45 degrees. It has to be negative 45 degrees. A decade below that, which is 0.005, it's at 0. Put an X there. A decade above, which is 0.5, you have to go a decade above the 0.0, which is 0.5, and that's why I labeled this 0.5 in, and I labeled this 0.005 in, because it gives me this point, and it gives me this point. I put my dashed lines in, because that's the contribution because of my pull. Here's my contribution angle because of my pull. What about my zero contribution? Well, I know my zero contribution is at 0.2 radians per second, it has to be at plus 45. There's my 0.2, I come up, I put an X at plus 45. A decade below that 0.2, which is 0.02, I have to be at 0. A decade above that 0.2, which is 2, I have to be at plus 90. There's my zero phase angle contribution, gone from 0 to plus 90, and at the break frequency, it's at a plus 45. Just like my pull went from 0 to minus 90, and at the break frequency, it was a minus 45. Now I have to add these to get the composite. Well, I usually put dots in where the composite is going to be, so I know there's a dot here, because nothing comes in except the 0 degrees on the angle until I get to this point here. At this point here, the only contribution is coming from that pull. So I know it's at this point, I know I have solid dots here the whole way down to this point. So I know so far I'm like right like that. That's my phase angle. Now, at this point right here, somewhere in this area, this is contributing. This starts to contribute. Maybe it's up in here a little bit more. But this contributes. Let me get another endpoint. Way out here, my 0 at 2 radians per second, whenever my 0 is done with, I get a full 90 degrees, and that's taking out this minus 90 degrees, so I'm at 0 there. So I know I have a point somewhere in here. Let's take a look. I know I have a point somewhere, I don't know, somewhere in there. And it starts breaking back up maybe. So my actual curve may look like this. So there's my response, my phase shift response for the overall system. At the lower frequencies, there's no phase shift. At the higher frequencies above 2K, not very high, but at 2 radians per second, it's back to 0. And I almost hit the minus 45 degrees, somewhere between, I don't know, maybe 0.3 or 0.03 or 0.04 up to the 0.05. In that area, I get close to a minus 45 degree phase shift to the sinusoid input to output waveforms. We've done that in a lab before when we did that one op-amp lab showing that gain of minus 60 there, where we had a phase shift on between the input and the output there. But that's what the phase looks like. Now, if you did that accurately, what you're able to do, again, we take a look at the next page. Let's use the Bode plot to find the voltage gain in dB at 0.1 radians per second and find the same phase. Okay. Well, if you did that, I got somewhere around, I think when I looked at it, I got somewhere around minus 6 dB. Stop the video and see if you get about a minus 6 dB at 0.1 radians per second on the magnitude plot, and a minus 36 degrees at the same 0.1 radians per second. Now let's hold on to that for a minute. Let's go down and let's find T of S. Let's use T of S to find the actual. Let's find the actual values of these and see how close they are. Here's my transfer function. I'm just substituting in J of 0.1 for S. Work through this, I get my transfer function being 0.5 at an angle of minus 36 degrees. So my voltage gain in dB is 20 times the log of 0.5. I get a minus 6 dB. Pretty accurate. My angle was a minus 36 degrees, actually. Depending on how accurately you did the phase plot, You can come up here and you can take a look at that. At point 1, I come up point 1 somewhere and I look. You're in that area right there, coming across. Again, depending on how accurately you did it, you can see where you're at. You're somewhere around minus 34, minus 35, minus 36, 37, or 38. You're in that area. So there's the first 4 examples, which should give you a pretty good idea of how to use the Bode plots, but we still have to show you how to handle single poles or zeros at the origin. I don't know if you remember that, but we have single S terms. We were case 3a and 3b. Well, really case 1. Case 1 was the constant term. Then we jumped to case 3a and 3b. We skipped over the case 2a and the case 2b that had single S terms in the numerator and single S terms in the denominator. You have to handle those a little bit differently. And we're going to do that in example number 5. And let's see, example number 6, which will show you how to handle those. So that concludes this lecture.